Today we're going to take a quick look at an introduction to acids and bases, as well as the reaction of acids with some metals. So acids and bases can be defined in several different ways. We're just going to look at the more basic definition right now, no pun intended, which is probably the one that you learned when you were studying acids and bases in middle school. Acids are defined as a substance that produce H plus ions in water, and bases produce OH minus ions in water. So acids and bases both dissociate when we put them into water, acids producing specifically H plus ions, the hydrogen ion, and bases producing OH minus ions, the hydroxide ion. The H plus ion, when we are dissolving the acids in water, we can think of the H plus ion attaching onto a water molecule, giving us H3O plus. So we sometimes say acids produce H plus ions in solutions. We sometimes say they produce H3O plus ions in solution. It's pretty much interchangeable as far as what we're going to be talking about. The H3O plus ion is called the hydronium ion. Both the hydronium, H3O plus, and hydroxide, OH minus ions are listed in your table of polyatomic ions. When it comes to the properties of acids and bases, we're going to be talking a lot about these. Now, we're not going to be tasting acids and bases in the lab, but unlike many people tend to assume, not every acid, not every base is deadly. They're found in common household items, including foods. Acids, when you taste them, they have a very sour taste to them, like lemons with the citric acid or vinegar, which has acetic acid. So they have a distinctive taste to it. Bases tend to have a bitter taste to it. So if you've ever had an antacid for heartburn, that often has a bitter taste to it from the bases that are in there. Bases also tend to feel very slippery when you touch them. So if you are to get a base on you, you'll feel like there's soap on your hands or something like that. Bases actually do react with fats and oils to form bases. Acids will react with many metals, and we're going to take a look at that on the next slide and then do a little experiment with that. One thing that I do want to point out here is that both acids and bases are electrolytes. Remember, an electrolyte is something that dissolves in water to produce ions so that an electric current is able to flow. Up until this point, we've said ionic compounds are electrolytes, nothing else is. And many acids and bases can be ionic compounds, but there are some that are not ionic, but they still dissociate in water. Again, by definition, acids have to form an H plus ion, bases have to form an OH minus ion. So there is dissociation going on. They are producing ions, which means they are going to be electrolytes. When it comes to the reaction of an acid with a metal, it's going to do a single replacement reaction. And if you remember back to our chemical reactions unit, we use table J to determine whether or not a reaction will take place. We're going to be able to write those reactants and products regardless of whether it takes place or not. The example that we're going to look at here is magnesium plus hydrochloric acid, HCl. So the first thing we want to do is this will be a single replacement reaction. So we need to think about the charges on the different ions that can form. Now, magnesium over here is an atom, but when magnesium forms an ion, which it will in this reaction, it's going to form a positive 2 charge. HCl, the H forms a +1 charge and the Cl forms a -1 charge. So when we go to rearrange these, the Cl has to go with the other positive ion. I can't combine magnesium and hydrogen because they're both positive. So I know that on the product side, hydrogen is going to be kicked off by itself. The magnesium is going to be with the chlorine. Now, this is an ionic compound. To figure out the subscripts for an ionic compound, I want to look up the charges, which I've already done, and crisscross them. So that +2 tells me I need 2 chlorines. The -1 tells me I need 1 magnesium. So we're going to form magnesium chloride as the ionic compound. And then hydrogen is off by itself. But remember, hydrogen is one of those 7 diatomic atoms, or diatomic elements. So because it's a pure element here, we do need to have that subscript of 2. And then to balance up the equation, we're going to put a coefficient of 2 in front of the HCl. So that's just predicting what the products are going to be for a single replacement reaction. We still need to determine whether this reaction will take place or not. In order to do that, we want to compare the 2 elements that are switching places. In this case, we have magnesium switching with hydrogen. And if you remember, the things that are most active are at the top, the least active are on the bottom. So we know that magnesium is more active than hydrogen. This means that magnesium wants to be part of the compound more than hydrogen does. Over on the reactant side, it's not part of the compound yet. And it wants to be there more than the hydrogen, which is part of the compound is. Which means magnesium is going to be strong enough to kick the hydrogen out of the way and take its place in the compound. So since hydrogen is so close to the bottom of this table, all of these metals are going to react with acid. So most metals will react with acids. The only ones that are listed here that will not react with an acid are these 3 down at the bottom, the copper, silver, and gold. Those are very, very non-reactive. So they're going to tend to not react with much of anything, including the acids. Now, I did use HCl here as my acid. It could be any other acid that I want to use. We're just comparing the hydrogen from the acid, which the acid has to have by definition, to the metal that it's trying to replace. And we're going to go over and do a little lab, and I'm going to show you some combinations of acids and metals and see what reacts and what doesn't.
So here I have some metals set up in a well plate. We've got some magnesium, some iron, some zinc, and some copper. And we're going to look at how each of these reacts or doesn't react with sulfuric acid, which is H2SO4, and with hydrochloric acid, HCl. So I'm going to take this and I'm going to put some sulfuric acid in there. And hopefully you can see, let me add a little bit more, that bubbling that's taking place there. So there is some fizzing, some reaction taking place on that one. And the same thing with the iron filings. And with the zinc, if I can get rid of some of this glare, you should be able to see that there's fizzing in each of these 3. So there's some really tiny bubbles there, here, and here, but there's no bubbles forming in this one. So the sulfuric acid is reacting with the magnesium, it's reacting with the iron, and it's reacting with the zinc, but not with the copper. So now let's take some hydrochloric acid and do the same thing. So you can see the fizzing taking place with the magnesium. Again, there's some fizzing with the iron filings as well. Some fizzing taking place right on the zinc. I think you can see a couple of those bubbles forming. and then nothing on the copper. So both of these acids react with the magnesium, with the iron, and the zinc, but not with the copper. So the type of metal does not determine, the type of acid does not determine whether or not a reaction will take place. All of these metals would react with any acid, or the ones that are reacting with these would react with any acid, and the ones that don't won't. So using table J, you can predict whether a metal will react with an acid or not. You don't need to know what that acid is, just the relative position of the metal and the hydrogen ion that it's trying to replace.